we really appreciate your attendance. I'll just give a quick overview of what my name is Johnny, and I'll be taking the first part of this workshop. So the first part is very introductory, it's very basic, and it's kind of catered to people that have like a little understanding of basic statistics and whatnot. And then Daniel, you might have seen him before, he'll take the more advanced part where if you do have experience with machine learning, you are kind of up to date with that kind of thing. He'll go through some really cool stuff with that. So yeah, the first part, I'll just be going through some very fundamental stuff, which is really important when you're dealing with any kind of data analysis. Cool. So just a note before we begin, please don't take photos or videos. Nicholas is recording, so we will have this on YouTube available to everyone. Cool, so first thing I'm going to talk about briefly is just what is data? What kind of data is available to us as the world? And we just have a few kind of examples here. In the top left, we have what we kind of usually call a rectangular data set. So that's one with columns and rows. It's very neat. If you've worked in Python, for example, it's a data frame. R as well, it's a data frame. And that's probably the nicest form of data to work with because it's very structured. On the right here, we just have some more examples of rectangular data. We do have example of missing data, which is something that just any real-life data set will have. It's not always going to be as clean and complete. It's going to have errors. It's going to be have missing values. And these are kind of the stuff that we'll deal with later in the course. Down at the bottom left, we have text data, so things like Twitter. And this is a bit harder to work with because it's not as structured as a set number of columns and a set number of rows. But it can be a lot more informative. So if you guys have heard of things like word2vec or glove word embeddings, that's using text data, and you can do some really cool stuff with that involving things like natural language processing, which as you will go through in the later part of the course as well. So stick around for that if you want to figure out how to analyze natural language. And finally, this could represent two things. It could represent an image, for example. And with images, you can try and do stuff like classification. So build a model that classifies this as a city, or maybe within this image, try and put a box around all the buildings and things like that. And again, that's going to very complicated AI models, and that's something we'll look in later in the course. But it can also represent city data, so things like traffic congestion. The government, for example, has data on Opal cards, and you can just think about ways of using that data to, say, improve the allocation of buses around the city. So the world is kind of surrounded by data. The techniques have always been there, but what's really exploding now is, well, the techniques as well, but also just the collection of data and the availability of data these days. Cool. So let's start off simple with some data. And let's start with just one thing, and that's just the height of everyone in this room. Now, if I have that data, how would I go about trying to understand it? Thank you. So, one way of doing that is we can plot what's called a histogram. Now, this is very, very important in statistical analysis. And the way it works is I'll go around the room, I'll ask, what is your height? And then you'll give me a number, and I'll plot. Whoa, oh yeah, you can touch screen. Sweet. So I'll just put a data point at your height, whenever those two things match, I'll just stack them on top of each other. So you can see there's a few people, like this is obviously like a dummy data set, or not actually the height of people in this room, but you can see a lot of people have heights around here, and then it kind of just dies off towards the tails. Yeah, or it could be normally distributed. That's something we'll get into later, because it's, yeah. Anyway, I'll just stay with something more basic now. And we can say split that across genders, so difference between the height of males in the room and the height of females in the room. Now in this room there's only one female, so just the one data point, but if we have a bigger sample it might look something like this. So generally what we call this is, we call this a distribution because it's a representation of how the heights are distributed across some population. And how can we compare two different distributions like this? So the height of males in the room and the height of females in the room. How can we compare that? Let's see. Well, there are some things called summary statistics, which tries to summarize the data quantitatively, so you can compare kind of exactly across the two data sets. So with, okay, back. Oh, do I have to press that? I don't know how to press back. So with this, we can obviously plot the two things and just visually look at it and see what is the difference. But if we can't kind of assign numbers to it, then we can't have any precise comparisons between these two data sets. So what I'm going to introduce are summary statistics, which does allow us to have these precise comparisons across distributions. So the first one you should probably be familiar with, it's the mean, also known as the average. And to calculate it, you just sum everything up and divide by the number of observations. So when you see a bar across something, that normally means that means it's the sample mean. So it's very good to be able to understand this kind of statistical notation. So I'll be introducing a bit of that. So this is something that even if you do understand the concept of an average, you might not know the notation. This means the sample mean. So if I take the average height of everyone here and divide by the number of people here, then that's the sample mean for the height of people in this classroom. Cool. And obviously a mean is a locality measure, so it measures around what number the height is distributed around. So with male and female, you can see if I kind of plot the histograms over each other, males tend to have a higher mean than the females, which essentially means that males are generally taller. Modality. So what the mode is the number that occurs most often in the data set. And with a distribution, you can have different types of modality. So before when we just had two graphs of male and female, hey, we have another data point in the female. Yes. We had something called that's unimodal, which means there's pretty much only one peak. There's only one number that's kind of clearly above the rest. Whereas in this instance, we have something that's bimodal, because there seems to be two peaks. So instead of splitting by male and female, if I just take the distribution of height in this room, it could end up looking like a bimodal distribution, because there'll be a clusters of female heights around the lower peak and a cluster of male heights around the upper peak. Sorry, Daniel. So what the median is another locality measure, and it is the point such that the number of observations lower than that point is equal to the number of observations above that point. So if this was a symmetric distribution, then the median and the mean would be pretty much the same. However, if it's skewed like this, and skewness is something I'll talk about later on, if it's skewed, then the mean and the median can differ by quite a bit. Now, why is this? Now, what do I mean by skewed? It means there's just a lot of data points that are, in this case, really, really high. And because with the mean, you're taking the sum and dividing by the number of observations, these data points tend to drag the mean across to a higher end. But with a median, it doesn't matter if the points are really, really high or if they're just above the median. It treats it as kind of the same, because it's just the number of observations greater and the number of observations less than. So the median is not prone to being dragged away by these high data points. So that's one of the properties of mean and median that's really important. And that's something you need to think about when you are trying to describe a data set. Do I want to know the mean or do I want to know the median? So the median is generally what you kind of expect, but the mean will kind of reflect if the data set does have really high or really low values. Next, so the mean and the standard deviation are probably the two most common and very important ones. I'm not going to go through the mathematics behind the standard deviation in this hour, but you can conceptually think of the standard deviation as how spread out the data is from the mean. And as a general rule of thumb, approximately 2/3 of the data lies between the mean plus minus one standard deviation. And approximately, I think it's what, 95% lies within two standard deviations. So
if it's normally distributed.
If it's normally distributed, yeah. So as I said, rule of thumb, it doesn't always work, but you can generally think of it as that. So if the standard deviation is very high, it means that the data is very spread out. And if it's very low, it means it's very clumped towards the mean. And standard deviation is denoted by the sigma symbol, and it's equal to the square root of the variance, which is denoted by sigma squared. Yeah, and here's just an example of each distribution. So you can see here, this one has a standard deviation of 5, and compared to the two other ones, which has the same mean but a higher standard deviation, the data is more clumped together when the standard deviation is small. Cool. And the last summary statistic I'll talk about is skewness. And I mentioned this kind of earlier. So what a skewed data set means is that it's not symmetrical around the mean. There tends to be like what's called a heavy tail. So here there's a heavy left tail, also called a negative skew, and here is a heavy right tail, also called a positive skew. And this is called a negative skew because there's more data points in the really high negative regions compared to the positive regions. So you can see here, as it goes towards the right, it cuts off quite drastically, whereas when it goes to the left, it kind of continues on, and it kind of extends out. It's skewed towards the left. This is something that when a lot of people look at first, they might get a bit confused. A lot of people tend to think that this is a right skew, but it's a left skew. And you always look at the direction of the tail, not the head. Cool. So that was some summary statistics for if you just have a single variable. Now let's look at what happens when we have more variables. So what is the height of everyone in this room and the weight? So if instead of just collecting the data on your height, I collect the weight as well, how might that look? So it might look like this. And this is what's called a scatter plot. So each point will represent one person, and that person's height will be represented on the x-axis, and their weight will be represented on the y-axis. So what can we say about this plot? Well, generally it seems to be kind of a dependence there. Like if height increases, weight tends to increase as well, because you can kind of see there's this positive relationship. And that makes sense. Like the taller someone is, the more body they have and the more mass they have. So how can we, again, it's all well and good to kind of point out that relationship and look at it visually, but how can we represent this numerically? So there's a couple ways of doing that, and the three that I'll talk about are covariance, Pearson's correlation coefficient, and Spearmans Rank correlation coefficients. So the most commonly used one is the Pearson's correlation coefficient, but I'll give a brief overview of the other two as well. So again, I'm not going to go too much in detail with the mathematics of this, but this is the formula for calculating the sample covariance. If you remember from before, I gave you the formula for the standard deviation, from which you can get the formula for variance, and it's very, very simple. Like if I want to calculate the variance of something, instead of having x and y, I just have x and x. So this becomes xi minus, and again this x bar means sample mean. So xi minus x bar times, again, xi minus x bar. Or in other words, xi minus x bar squared. So the covariance and the variance are very related. So this kind of measures the direction in which the data moves. So if the xi is generally greater than the x bar, then it means that, if when xi is greater than x bar, yi is also greater than y bar, then this will be a positive, and this will also be a positive. So we'll end up with something positive. And if xi tends to be less than its mean, at the same time yi is less than its mean, they'll both be negative, and two negatives multiplied together will give a positive. So what does that mean? That means if the data moves in kind of a similar direction, then the covariance will be positive. And conversely, if the data moves in a negative direction, so if as xi increases, yi decreases, then one of these will be positive, one of these will be negative in general, and you will end up with a negative covariance. So we can definitely use the covariance to kind of measure the dependency between two data sets. However, a problem with the covariance is that it does depend on the natural variance of each point. Which means, say I compare the covariance of height and weight to the covariance of, say, height and, I don't know, hair length, for example. Each one of those variables will have a different variance, and that's going to affect what the end covariance is. So a higher covariance doesn't necessarily mean a higher linear dependency if we're looking at two different variables. So what are some ways of overcoming that? We can use the correlation coefficient. So there's different types of correlation coefficients. Generally, when someone says correlation coefficient, they're referring to the Pearson's correlation coefficient, and that's the one that's most commonly used. So this is the formula. It's the covariance divided by the standard deviation of both variables. So if you remember what I said just then, the covariance is affected by the natural variance or standard deviation of each of the variables. So this is a way of standardizing it and kind of removing the effect of that natural variance. So what the correlation coefficient is a number between -1 and 1. So when it equals 1, it means there's a perfect linear dependency between the two variables. And if it's a -1, it means there's a perfect negative linear dependency. If it's 0, it means there's no linear dependency. And notice how I've been saying linear dependency, because that's what the Pearson correlation coefficient measures. If there's a dependency but it's non-linear, it can still have a correlation coefficient of 0. So this diagram demonstrates really well what the correlation coefficient is. So you can see here, when it's a perfect line and it's kind of moving in the upward direction, then the correlation coefficient is going to be 1. Over here you can see there is a dependency, but it doesn't lie on a perfect line, and that means it's still positive and it's still quite high, but it's just not going to equal 1 because it's not perfect. And as you can imagine, as the correlation coefficient goes towards 0, the dependency is a lot looser. So it's really about the strength of the dependency. Over here, this is something that's also important. The slope of the data doesn't matter. It's about how close it is to a perfect line. So notice how the slopes on these three things are all different, but the correlation coefficient is still 1 because there is a perfect linear dependency. So that's something really important to keep in mind. The slope, the correlation coefficient doesn't tell you anything about the slope of the relationship, it tells you about the strength. And it tells you the strength of the linear dependency. So you can see here in the bottom, these two variables are very clearly dependent, right? We have something that's kind of wavy, we have a nice diamond. There is a pattern in this data set, which means there is a dependency. But because the correlation coefficient measures the linear dependency, all these things will have a correlation coefficient of 0. Cool. And last thing I'm going to talk about is Spearmans Rank correlation coefficients. So with the Pearson correlation coefficient, it's just looking at the values. So remember, it uses covariance, and covariance looks at each individual value and compares the values. Now what the Spearmans Rank correlation coefficient does is it compares the rank of the data instead of the value. So what that means is if you kind of line up the data by order of rank and say, okay, I'm going to line you all up according to height, and then I'm going to line you all up again according to weight. Now if that ranking is the exact same, then the Spearmans Rank correlation coefficient will equal 1. So it doesn't matter if one guy, we just have a massive 7-footer here, and his weight is it's still the biggest, but it's not massively big. That won't affect the Spearmans Rank correlation coefficient because it doesn't look at the values, it just looks at the rank. So here we can see that the rank of y and the rank of x are the same. The biggest value in y is also the biggest value in x. The fifth biggest value in y is also the fifth biggest value in x. So there's a perfect Spearman's correlation. But if you look at the values themselves, it's not a perfect linear dependency, so the Pearson correlation coefficient is not 1. So when would you use one over the other? It really depends on what you kind of want to do. I guess what I'm trying to do is just expose you to a few of these measures so you know what tools you can use if you're trying to do some analysis. Cool. So why do we actually need to visualize? I've shown you all these measures that you can use to compare between data sets. And these are very precise. These are numerical. You can do calculations on them. Why should we visualize something if that's more subjective and it's a bit more wishy-washy? Well, here is one perfect example. It's called Anscombe's quartet. I don't actually know how to pronounce Anscombe, but I will give it a go. But anyways, you can clearly see that all 4 of these data sets are very, very different. But what they have in common is that the mean of all the y variables are the same. The mean of all the x variables are the same. Has the same standard deviation for all of them. It has the same correlation coefficient for all of them. So that is a perfect example of why we need to visualize, because these summary statistics are, a summary. It doesn't tell you the whole picture, and no summary statistic ever will. The only way you can kind of really understand what's going on is to see the whole picture yourself. And the easiest way to do that is to visualize it. Because if I showed you the summary statistics of all 4 of these, then they'll be the exact same. And without any other information, you could argue that the data sets are very, very similar. But as you can see, they're not. So what are some ways we can, say summary statistics. So why do we want to visualize data? Fast pattern recognition. So if we see something, like if you remember those diagrams below, we saw a pattern but it had no correlation coefficient because there was no linear dependency. But if you plot it, you can clearly see if there's an obvious pattern around. You can see if there's any outliers. So for example, can go back. So for example, in this plot, it's a perfect line except for that data point. And if you remember what I said at the beginning of the lecture, your data is not always going to be clean and accurate. So if you come from a science background and you have a measurement that looks like this, then you will generally need to exclude that from from your analysis. And a very easy way of seeing if your data does have very obvious outliers is to plot. And same with this one, that looks like an outlier as well. Variable interaction, so yeah, what the dependency structure between two variables is. It's often a lot clearer to see that in a visual rather than a summary statistic. So if I tell you something has a correlation of 0.8, that could still look like a whole number of things. It will give you an intuitive understanding of the data, and then if you decide to fit a model to it, you can explain why you did that. So if the data looks like it's kind of exponentially increasing, you might fit an exponential model to it, and you can justify that by saying, okay, I looked at the data, I understand what it kind of looks like, so I'm trying this particular model. So here are some examples of some cool visualizations. So the first one is if you just have one variable, a histogram is almost always your starting point for that. Second one is if you have two variables, a scatter plot is almost always your first, your go-to visualization tool. And then the third one actually has 4 variables on it. It's a 3D scatter plot, and each, actually no, it has 4, yeah, it has 4. And for each data point, it has a different size and color depending on the power. The size might actually be another variable. So this could theoretically have 5 variables in this one plot. Beyond that, it's a bit hard to visualize things. Like it's hard to pick 6 things to change in a plot to represent 6 different variables. And not only is it hard to represent, it's also hard to interpret because you'll be having to like switch between a lot of things. So later on in this course, we'll look at some dimensionality reduction techniques. So what that involves is if I have a data set with, say, 20 variables, can I get that down to 10, for example? And how can I do that? Well, one way is saying, like, if I have data on both height and weight, and they're both very correlated, like if I know someone's height, I can roughly know their weight, then maybe I don't need both variables. Maybe I can get rid of one and still have quite a lot of information about that person. So some examples of that, PCA stands for Principal Component Analysis, and SVD stands for Singular Value Decomposition. And I'm sure Daniel will go through the mathematics behind that, if not today, in a later course. So yeah, here's a, I guess, summary of what you would use if you have 1, 2, 3, 4, 5 plus variables to visualize. And yeah, here's just an example of what they might look like. So how do you visualize things? Well, you wouldn't draw them on pen and paper, you'd have to use some kind of software. So this is a chart taken from Kaggle. If you guys don't know what Kaggle is, it's kind of a data science competition website. Recommend you guys check it out. And they did a survey of what tools data scientists use in their analysis. So the most popular two are Python and R. And then you have things like SQL, TensorFlow, but TensorFlow is a lot more specific than Python and R. And then yeah, you have Tableau, which is mainly just for visualization, MATLAB, Octave, etc. So these tools have its own advantages and disadvantages. So Python is a much more general purpose language, so you can use it for a lot more things. R was built by and for statisticians, and it has a lot of packages that get into very specific statistical analysis. And what Daniel has done is he's kind of outlined which ones are good for visualization. So R has a very good visualization package called ggplot2, and that's my favorite visualization tool. Python's pretty good, it's got matplotlib and Seaborn. Tableau, as I mentioned, is kind of specialized towards data visualization. So yeah, the blue outline just means it has graphing capabilities, and The thick blue outline means it's very good. So I'm just going to go through kind of a few concepts of what you might do with the data once you find out what it looks like. So if it's skewed, often we want to make it symmetrical. Like there's a lot of good properties of having symmetrical data. For example, you could then check if it's normally distributed. So a normal distribution is a special type of distribution that pops up a lot in things like central limit theorem, which we'll talk about later. But yeah, one of the properties of normal distribution is that it's symmetrical. So if you can make something into a normal distribution, it will have to be symmetrical. But once you do that, you can do some nice things with it. One way of dealing with really skewed data is to take the logarithm of the data. And if you think about what the logarithm is, it's a graph that will increase quite quickly, but then it will kind of flatten out as the values get really, really big. So if you take a logarithm of this data, these really big values will kind of be pushed closer towards the cluster. And a lot of the times, if you log something, so this is just the log of all the values, and you can see it's a much nicer distribution. It's symmetric. You can see, like visually, you can see more of it because it's not. You don't have these data points down here that just have one or two values. You can see a good chunk of what's going on. And probably the last thing I'll talk about before I hand over to Daniel is what it means to be correlated. Now, correlation coefficient, as I said, is a measure of linear dependency, but one thing that you guys need to keep in mind is that correlation does not equal causation. Just because two data points seem to move in the same direction or seem to have some kind of relationship, it doesn't mean one causes the other. So something like height and weight, like it makes sense that there's a relationship between those two. So you can look at the data and say, oh, there is a correlation, it makes sense as a causation. But there's a really fun website called Spurious Correlations, and that's where this guy has just kind of pulled out two data points that are extremely correlated, but obviously have no causation. So the first one here, we have the data about number of people who drowned by falling into a pool, and number of films Nicolas Cage appeared in. So this has a correlation coefficient of 0.66, so fairly high, but obviously, well, I hope there's no causation behind this. Another one is the divorce rate in Maine and the per capita consumption of margarine. And this has a correlation coefficient of 0.99. So, you know, again, probably no causation there. So, I hope that was a nice introduction to you all and you got something out of it, whether it was doing summary statistics or ways of statistical thinking. I'm going to hand over to Daniel now, who will go through a lot more advanced topics, but I hope you guys come in later weeks where we kind of delve more into more technical stuff and we learn to do more cool things. Thank you.
I was going to mention, like, where is it? This thing, right? Like, you can see the correlation coefficient is like 1 for extremely positive relationships and -1 for extremely negative. So my question is, like, you know these ones, like the parabola, like the quartic and these planes and these parabolas, right? The correlation coefficient is 0, right? But, so my question is there some sort of measure which can capture the information in these graphs with not actually a linear relationship? So Spearman's correlation coefficient is if the rank increases, then the correlation should be 1. So that can capture like cubics which look like that. So my question is, how about these? So for example, parabola, right? We have a correlation coefficient of 0. So is there some sort of measure which allows you to have some sort of information like number? So this should be like 1 technically. Like it's not correlation, but this number, some sort of information number, should be 1 because it shows a lot of information. This one should be 0 because there's no information at all. Everything's scattered around. So my question is, does anyone know some sort of information number which can be used for everything. Like this should have a high information number. Also high. This kind probably low, right? Should be high. This one should be high as well, and this one should be high, but not probably that high. So does anyone know any number or concept? So there's multiple ways you can do it. The first one is called mutual information. So mutual information is the optimization cost for random forests. So they use it to categorize like these. So this one will have high mutual information, right? These ones will have low mutual information. It's a number from 0 to 1. Other ways you can do it, like you know these parabolas, right? What happens if you split the data into half and you do the correlation on one side and the correlation on the other side, absolute value, and then just add it up? That's another way, right? Because if you cut the parabola into two, this way will be like that, and the other way will be like that, right? So, yeah. So that's the other way. So then the other question is like, how many splits do you do the data like this, right? So you cut it into like 1, 2, 3 like splits, and then you calculate the correlation coefficient with every 3 parts. You can add it all up. That's another way. But mutual information is probably the stuff that you'll use. Yeah. Wait.
Daniel? For the first rank is 0, 1. It is more concentrated in the middle, but I think there is kind of some information in the data set.
Yeah.
Because it's more concentrated in the middle and less concentrated outside. The 0, 1. No, the first rank. Yeah. In the middle.
Oh, that one.
No.
What? Oh, yeah.
That one. The circle look like a circle. The one look like a circle.
Oh, that
yeah,
one.
that one.
Yeah.
It's more concentrated in the center than the outside of the circle. So there must be some information, right?
Interesting. So you're trying to say, okay, so the majority of the data is, yeah, okay, although the majority of the data is clustered into the center, well, it still looks like a cloud, right?
You'd expect that with two normal distributions, right?
Yeah.
Completely
It's
unrelated.
more about, can you use information from one variable to tell you about the other?
So like if like for example, if something increases, do you see any increase in the other? Yeah, that's kind of like
a
that.
circle, so it's not necessary that if one is increasing, the other will increase as well.
Yeah, something like that. But like for these ones, right, you can clearly see if one increases, right, it depends on where you are. Like if one increases, right, then this will increase. But this one is like, for the whole area, when you increase something, nothing will increase. Kind of, like if I am, yeah?
Have you seen Naruto?
Naruto,
Yeah.
what about it?
You know the Rinnegan? There's like lots of circles inside circles, right?
Okay.
What if a data set was like that? Is there some kind of information you can gain out of a data set that looks like that?
Yes, mutual information probably will say something about it. However, so it's like circles within circles.
Yeah.
If it's on a, like a 3D scale, then what you can do is you can actually push it down to one level. So it'll look like a concentric circles. And then with that, mutual information probably will say something about it. Although I'm not sure. But yes, there are measures which allow you to like say, oh, this concentric circles and stuff will have information.
So you might be able to like use mutual information for that data set that he just said. Like, you know, if it was like really high density in the middle and then less density, but there was like an even pattern in which the density decreased.
Yes. If it's on 3D data, probably yes. But if it's on 2D data, yeah. If it's extremely clustered and you can see like clear, like this one's not that clear, but if you can literally see like a big cluster in the middle, and everything is like, you know, smoothing out, there should be some mutual information. But if it's for this one, I'm just saying like this one probably doesn't look like anything. But yes, you're right. If there's lots and lots of heavy density in the middle, and it keeps going down, you can literally see the graph just keep, you know, increasing, then there should be some information.
Another thing you could do is you could transform the data, say if it's concentric circles, you can have some kind of linear transformation to transform those circles into, say, lines, for example. So if you just kind of change the space around which the data is represented, you could then use some more traditional measures such as correlation coefficient. But that's a bit more of a manual process. You kind of have to notice, oh, this looks like a circle. I'm going to try transforming the data from a circle into a line, for example. Another technique which is pretty advanced is called a copula, and you guys can read about that yourselves, but that allows you to measure some non-linear dependencies. So copula, sorry?
How to spell it?
Copula, C-O-P-U-L-A. But
But the other, like there's other methods, like if you fit a model onto it and then you get the feature importance, for example, that's also another way you can do it. There's also like Shannon entropy, something information, something, can't remember. Why is there no internet? Is it like no internet? Or is it like just slow? Oh, this is not working. There isn't. Okay, so probably just Kaggle. I think Kaggle server is not working. Well, that's fortunate.
I'll see if it works on my laptop.
Oh, but this is like the UNSW one, right?
Yeah, that does some work.
I don't know. I'll just open. Wait, is it still loading? No. Why is this? What? Okay, data sets. Okay, well, it doesn't seem like it's... Yeah, but anyways, I was going to use Kaggle, so there are two options for you to use when you do programming in Python. The first one is actually, well, three, kind of. The first one is to install Jupyter Notebooks, which is, I highly recommend. You have to, actually. No option. But there is a new version called Jupyter Lab, which is a very, that's way better. The other one is to use online Jupyter Notebooks. So Kaggle is for free. If you register as an account, Google bought Kaggle, just for interest. Oh yeah, the server's down, whatever. So kernels is the stuff that you'll use for online. So if you don't actually know how to install Jupyter Notebooks, you can just use online. Everything is interactable within Google Chrome, Edge, Firefox. Yeah, any browser should work. The other option is to install Python, as a standalone programming language. Although I don't recommend that because data science, we're not going to use. Well, you can use text editors, but I don't recommend that. Sorry?
Anaconda is good. It comes with.
Yes, Anaconda, yeah. So that's the Jupyter Notebook, Anaconda, yeah.
It comes with all of that.
Correct, yeah. So yeah, it comes with the
NumPy, SciPy.
everything, yeah. So yeah, and the packages you have to install, I think I wrote it down was pandas, NumPy. Oh, whatever, I just wrote it down somewhere. It's a long list. There's lots and lots of packages. Oh, this is okay. Well, I was going to show you programming today, but it seems like Kaggle's server is a bit dead. So I'll show you something else instead. Well, this was what I was going to do later. Did you see this diagram? I posted it up I think yesterday or something. So actually, there was actually supposed to be another diagram. I actually didn't post that because it couldn't fit. So so this diagram highlights the. So the question is, I was having a question before, okay, machine learning, artificial intelligence, okay, whatever. These algorithms here, there's algorithms there. How they're all interconnected? Is can machine learning actually be written in one textbook and it's connected everything? So that's the question. And so I'm not sure. I tried to find diagrams online, but there was actually no big diagram which highlights all the connections with everything. Although we're still trying to develop that. So has anyone heard of singular value decomposition? Heard of it? So
I don't understand.
okay. Singular value decomposition. The theory says that every single matrix, so any single table of numbers, literally anything, can be decomposed into three components. I'll talk about that later. But these are the three components: U, sigma, and V transpose. Okay, so the most important key concept is any single matrix can be decomposed into these three components. Okay, any. No matter if you have negatives in your matrix, no matter if your matrix is a long line, it's not like a table. Any single table or matrix can be decomposed. That's the key getaway. So has anyone heard of pseudo-inverses? So the question is, this matrix tables of numbers. If you want to compute the inverse of something, so you want to. What inverse means is if you get some sort of table of numbers, you times it with with the original table of numbers, but inverse it, you should get a matrix of the identity. So the diagonal is all 1, everything is 0 everywhere else. So it's 1 times 1, it's 5 times 1 over 5 is equal to 1, right? Something like that. So the pseudo-inverse says that any single matrix, any single table, if it's a row or a column, I don't care, can have an inverse, right? Because sometimes in maths, you can't actually take the inverse of something, right? If the determinant is 0, right, you can't take the inverse, right? But even if the determinant is 0, you can take the inverse. So it's called a pseudo-inverse. It's an approximation of the inverse. Last week, we talked about Markov chains and Markov systems in the advanced course. That's for simulations. So singular value decomposition is actually related to eigenvalue and eigenvector decomposition. Actually, they're technically the same thing, but with eigenvalues and eigenvectors, you probably learned it in maths or you probably don't know about it. But it's the so I think most people would like think, what the hell? Like, what am I going to use eigenvalues for? Like, well, it's just maths. I just have to do it for like maths. But you never will use it in real life. But in fact, you will use it. So Markov chains, for example, if you want to take like, remember the Markov system was every single 5th step, you want to times the matrix by 5 to get the 5th iteration of the simulation. Instead, like the problem is you actually have to times the matrix 5 times, like matrix 1 times matrix 1 times. Instead, if you use eigenvalue decomposition, you don't need to times the matrix 5 times. Anyways, has anyone heard of principal component analysis? Yeah, okay. So, no? Okay, principal component analysis, like as Johnny would explain, was if you pretend you have 1 million columns, right? Or 10 million, like big data. The question is, how are you going to visualize it? Or how are you going to capture information with smaller dimensions? Right, so humans can't visualize 10 million dimensional data. So the question is, can we like compress it into like 3D? Yeah. So that's what principal component analysis does. It compresses your data from 10 million dimensions or whatever n dimensions into some sort of like minimum dimension. And you can use singular value decomposition. So singular value decomposition, in my opinion, is the mother of all algorithms. Like it's the stuff which you, well, obviously matrices, but who cares about that? And cost optimization. But that's the technique which underpins nearly everything. So the next one, have people heard of linear regression? That should be.
Yes.
So linear regression is just fitting a straight, well, it doesn't have to be straight line. You're fitting some sort of line to your data. So in fact, you can extend this in any number of dimensions, right? 10 million dimensions, I don't care, whatever dimensions. Linear regression will fit some sort of straight something. It doesn't have to be a line. Just to be sure, you can fit a parabola with linear regression, right? You can fit a cubic, a quartic, whatever, right? You can fit a logarithm, an exponential. The problem which people get confused is linear means, so do people understand actually why it's called linear, but you can actually fit a parabola to it? Yes. So yeah. So all the coefficients have a degree of 1. So yeah. Well, actually, a better way to explain it is actually so if you pretend you fit some sort of parabola or line, right? The cost function that you're actually going to use is linear, right? Because it's like a direct line. The error is a line, if you get what I mean. And the coefficients have to be positive. Well, it's not. It's first degree. So there's no squares, there's no cubics for the coefficients, right? Not the actual line. Anyways, I'll explain that later. But so the someone was asking us to do confidence intervals and prediction intervals. Actually, yeah. There is a formula for confidence. So what is a confidence interval and a prediction interval? So pretend you do some sort of prediction, like you predict weight with height, right? But how accurate is your prediction, right? So if I say your height is like, if your height is like 180, your weight is like 60, how accurate is the prediction? So is it actually 60 or is it like 55 to 65? So what's your range of actual predictions? So that's what the confidence interval and prediction interval capture. We'll talk about that in the advanced way of the time. Yeah. Has anyone heard of lasso regression? Or L1 regularization? There's also ridge regression. Okay, so what lasso regression is pretend you have 10 million dimensions, right, of the data, and you fit a linear regression to it. Right, maybe only 10 actually do something, right? The other 999,990, right, they don't do anything. There's like like we did the correlation, maybe there's like no correlation at all. What lasso does is it makes the non-contributing ones all to 0. And only the 10 most important features have some sort of number attached to it. Right, so if you don't know what I'm saying, like what I mean is like linear regression is something times weight plus something times height plus something times energy plus something times blah. So like something times, like, I don't know, weight plus something times height plus something times age plus something times income, right, is equal to your happiness, for example, right? Right, so these variables, right, it doesn't have to be like these four, just pretend you have like the whole world's data, like it keeps going, keeps going, keeps going. Well, so linear regression is just just numbers, right, so maybe it's like 3 plus 4 plus 5 plus 6, I don't know.
Their
Just something
bias
like that.
variable.
Sorry?
Their bias variable should be plus be some kind of constant.
Time coefficients.
Yeah, coefficients. So like, if I write it, I'm not gonna write it in maths form. But yeah, so these are the, so the question is, right, so if I have like 10 million, like 10,000 of these columns, right, do you think all of them will have numbers attached to them? So what lasso regression does is it takes some of them and makes it to 0. So that's the lasso regression. Right? Ridge regression is sometimes these numbers, right, they get too large or too big or too small, right, or well, too negative and too, like negative 300 plus 4 or something plus 500 something, I don't know, something like that. So what ridge regression does is it tries to minimize your actual numbers, right? The sum of all the numbers, well, not really sum, the squared sum, is they want to reduce these numbers, these big ones, and they try to distribute all these numbers to all your 10,000. So in fact, ridge regression is kind of like the opposite to lasso. Lasso tries to make 10 most important, everything go to 0. But ridge tries to make everything distributed, right? So everything will be like 1 plus 1 plus 1 plus 1, la 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 la, right? So it's like distributing all your coefficients around. So it will be like, so all these 10,000 will be important there. So that's the difference. So the elastic net regularization is the combination of both. So they combine both the concepts of lasso, which is lasso is delete all the unnecessary columns and keep only the 10 most important. Ridge regression is distribute all the importance across in all of the variables. Elastic net is the average of both. It does the distribution of everything and the penalization of non-important features. So it's combined. Yep.
So lasso's I've seen before, and it's trying to combat the problem of overfitting your data.
Yep.
What's ridge regression trying to combat?
Ridge, okay, so it's kind of like the opposite.
So it's when you don't have enough
Overfitting.
variables, and that's what you're trying to combat? Or
No, so lasso is trying to, yes, combat, well, ridge regression also combats overfitting. But what it means, it gives importance not to one variable. Because if you give too much importance to one, maybe that's also overfitting. So but lasso does that. It gives importance to the 10 most important ones. But ridge regression tries to distribute your importance. So maybe like if one changes in ridge regression, it says that all of your variables have to change before something actually happens. Lasso says if only 10 change, then something happens. So ridge is like, so if you, where's the rubber thing? Oh, yeah, thanks. I'll show you. So, right, this is lasso or L1 regularization. This is L2, right? This is the number of columns. Oh, well, this is a column number, right? So like column number 1, 2, 3, la la la, right? 10 million or something, right? If you sort everything, right, the importance should look something like that, right? 2 and 0, nothing, right? That's lasso. Ridge regression tries to do something like this, right? It tries to give importance more to everything. It tries to even out the importance, something like that. So obviously not like that. It should look more like that, but something like that. So what it means is that they just want to shift the importance distribution like this way, right? That's L2, that's L1. And elastic net, it just averages it out. That's elastic net. It just averages the L1 and L2. Yeah? Does that kind of answer your question? Or not really?
Sort of. I just thought you, like, if you wanted to do that, you would just change your lambda in L1, and then you'd maybe get to the same thing. But that's why I was wondering why you'd need ridge in the first place, and what I was trying to solve. But I guess I'll research a bit, but that does explain it a little bit.
Okay, so yeah. Actually, I haven't explained the lambdas, but the lambda L1 is a number you can change. If you increase the number, you're penalizing more. If you decrease the number, you're penalizing less. So when you put it to 0, there's no penalization at all. It goes back to the So like, how do we go? Where? Yeah. But if you make the lambdas to 0, so you can actually change the number, everything will go to 0. Like, it will just go back to the original linear regression. However, the difference is lasso is just the sum of your coefficients. So if the coefficient was 3, 4, 5, 6, you just do 3 plus 4 plus 5 plus 6. Ridge regression is the square. So 3 squared plus 4 squared plus 5 squared plus 6 squared. What it means is that the large numbers will be penalized even more. Ridge regression tries to reduce the largest number. Lasso does not want to do that. Lasso tries to give larger numbers a bigger chance. That's kind of the... but no, if you increase the number of this and the number of this, it will actually be different. Because if you increase the magnitude of lasso by 1, you're actually squaring the magnitude. Kind of?
Yeah.
Elastic net just uses both. So averages both. There's also, who cares about that? I talk this all the time. Oh, yeah, one more thing and then the intro will finish, is there's more stuff. So I couldn't fit it on the page, but generalized linear regression is related to logistic regression. So logistic regression is just to classify if someone's like going to die or survive. So 1 or 0. Remember the regressions that we were talking about is continuous. Like if you want to predict the happiness of someone I read before, you have to add variables. Happiness can range from 0 to 100, right? But logistic regression is a number from like 0 or 1, right? It's not like a range. It's like a set. So like predict survival or something. There's also, has anyone heard of support vector machines?
Yes.
So support vector machines is a generalization of elastic net regularization. So in fact, support vector machines are related to linear regression. It tries to fit some sort of plane to your data, not a line, like some sort of plane. And then support vector machines are related to neural networks, so you probably heard all about neural networks. But neural networks, so does anyone have to explain what a neural network actually is? Or does anyone have a go at it, or should I just say it? So the problem is, I think people kind of understand what a neural network kind of is, right? It's kind of like some sort of big network of neurons, right, if it's your brain, and then you put some input in, and then it goes through all these bunch of neurons, and then it computes something, right? Something like that. That's a neural network. But the mathematical understanding is pretend you have some sort of table, right? I want to map it to some sort of dimension. So remember what I said PCA? What PCA does is it gets 10 million dimensions, and it reduces to 10. So what neural networks kind of is iterated PCA. Well, not really. But what it does is you get your 10 million columns, right? You reduce it to 100 million. Oh, sorry. No, you can increase also. Increase it to 100 million, right? So you kind of like do reverse PCA, if you know what I mean. And then you reduce down, and then you increase or whatever, right? So it's kind of like an iterated principal component analysis. Not really. That's just a better way to explain it. In mathematical ways, you just say it's a linear mapping. It's multiple linear mappings. You map from one space to another space to another space to another space and so on, right? And the activation function, has anyone heard of that? Oh,
Yes.
activation function. So that's the sigmoid activation function.
It's how to map from one layer to another layer.
Yeah.
In the hidden
So
activation function.
there's multiple activation functions that the sigmoid.
Value.
Yeah. What they are is so remember a linear regression is in fact a neural network, but it's no layers, technically. The activation function for a neural network is linear, so it's like a linear activation function is just a straight line, right? All negative values are negative, all positive values are positive, right? So a neural network, a linear regression is a neural network with 0 layers, but an activation function is a linear activation function. So a logistic regression is a linear regression. However, the activation function is a sigmoid. A sigmoid looks something like oops, that should be 0. That should be 0.5, something like that. and this is a 1. The ball's getting ugly, but yeah. Oh, they didn't draw it right. Tan H, and value. Anyways, we're going to learn about that. Okay, so the question is, what does an activation function do? So pretend that so linear regression is kind of like a straight line-ish, right? So the question is, can we make this straight line into like a parabola or some sort of other shape? That's what activation functions do. They change your straight line into like some sort of other shape. I think there was a theory, a theorem I can't actually remember. Any single function can be approximated by a neural network. Okay, any. I can't remember the theorem's name, but there's actually a theorem which says that. Okay, so there are two important theorems. The first one is singular value decomposition can decompose any single matrix. Okay, the key point is any single matrix into its components. And neural network is any single function can be approximated. I think I should end the introduction. I think I went over time. Yeah, okay, the introduction is kind of over. In the advanced one, we'll actually go into the details of this and the other stuff.